I want to talk about a strange confluence of technologies, of technology types that I'm starting to see, and this is a little bit unusual. I'm trying to come up with some vocabulary around this. I've been doing a bit of thinking about what this means and the impact that it's going to have on our industry. Well, let me start by just turning off the slides there for a moment. For the most part, I'm going to speak without slides and just try and invoke your imagination on a few things. So in terms of trends in computing, there are a couple of things that are buzzword compliant these days. Certainly we hear a lot of talk about the Internet of Things. What does the Internet of Things mean? As with most buzzwords, you can make it mean a lot of different things. But I think the best definition that I've heard so far, and unfortunately I didn't record where I heard this definition, is that the Internet of Things is about taking physical objects and making them also digital objects. So anything that is existing in the real world, the Internet of Things is about giving that a digital connection. That can be a sensor connection or a control connection, something like that. But the Internet of Things is a category of systems that we have long called embedded systems. That is the concept of a computer system embedded into something else. And there's obviously a huge range of systems that are embedded. And we're certainly going towards the low end with the Internet of Things. So let's just talk about that for a moment. The first embedded computer that I worked with had a single board computer in it. But at that time, single board computer was about the same size as a sheet of paper, roughly 8.5 by 11. So that was the embedded computer. And that system had, if I recall correctly, 48K of memory and 8K of ultravioletly erased memory, a ROM chip. And it was a fairly inexpensive system. It was a couple $100 at the time. These days, the low end of embedded systems is more systems like this. And this is a 96 boards device, a smaller form factor than what Grant mentioned this morning. This is the new IoT form factor for 96 boards. And as a development board, this is obviously much bigger than the device needs to be. There's a bunch of connectors on here whose sole purpose is to make it easier to program and debug and test using this device. But on there we've got a microcontroller. In this particular case, the microcontroller is an ARM Cortex M4. And you can go down scale from that. You can go a little bit farther down to an M0 or an M0 Plus, which is in fact a fairly really tiny microcontroller, but probably comparable or faster than that 8.5 by 11 board that I used all those years ago. Interesting thing about an M0, it's usually implemented with current or slightly older technology, a 45 or a 55 nanometer chip construction process. But if you took the M0 or M0 Plus design and you implemented it in a cutting edge process technology, made a cutting edge chip out of it with a 10 nanometer or 14 nanometer process. If I've done the math right, you could fit 2 or 3 of those processors stacked side by side on the edge of a piece of paper, on the edge. Let's think about that. You've got a spec that is like a third of a piece of a paper in dimension square. That's not even big enough to connect any wires to, let alone have it something that you can touch or mount or do something like that. So obviously that processor by itself isn't going to be implemented like that. It's going to have some memory, some peripherals put around it. It's going to have several thousand times larger set of connection pads added to it so that you can actually attach some wires to it, get some signals in and out of it. But imagine how much power that spec is going to need to operate. It's going to run on a really, really minute amount of power. And in fact, that class of processor can run off of ambient energy. You can take just the normal vibration of people walking past in a hallway or a car going down the road, or you can take heat that's escaping from a vehicle or a building, and it can pass through a device that collects a bit of electricity from that just ambient energy and stores it up, and then allows that processor to do things on a periodic basis. Take sensor readings and then report that. The real challenge is actually how you're going to report that out of there. The radio or the network connection that's going to report that information is the thing that's going to draw the power. The processor itself is almost an insignificant amount of power. If you want to think about applications of that type of technology, think about the sensor that you have inside the tire of your car. There's a sensor in each of the four wheels of your car. That most cars, there's an alternate way of doing this, but typically a modern vehicle will have a sensor in there, and it's a tiny little package attached to the valve stem. That package contains a microprocessor, an accelerometer, an air pressure sensor, and a small radio circuit. The power source for that is one of these lithium coin cells. So you've got something about the size of a quarter, and it's expected to have a 10-year life. This coin cell powers that computer for a decade. Obviously, really, really tiny power consumption there. What's the accelerometer doing inside your wheel? Why do you have an accelerometer inside your tire? If you think about it, almost all of us have our cars parked more than they're driven. Even if you are an avid driver, such as Evan Weaver, you're going to drive less than 12 hours a day on average, and most of the time that car is going to be sitting there not going anywhere. You probably don't care about your tire pressure when you're not driving. And so part of the approach to getting that battery to last a decade is to simply sleep when nothing's going on. When the wheel is not moving, you don't care. When the wheel is moving, then the processor takes that into account and it starts saying, okay, I need to report. I don't need to report the pressure continuously. I can report it every 10, 15, 30 minutes, and that's enough for the car. But the radio inside your tire needs to communicate with the frame of the car. And if it's at the bottom of its rotation, it's quite a distance from the little antenna that's mounted in the frame of your car. So it's going to need a fair bit of energy to broadcast a signal that can be received. So the device actually uses the accelerometer to figure out, based on the acceleration of gravity, where it is. And it does the broadcast at the top of the turn, so that it can use a lower powered signal to communicate with the vehicle. So this is an example of the low end, where we're going with sensors that just sip power, that use very, very tiny amounts of power. There's all sorts of interesting aspects to that. What happens when you have tiny sensors that sip power and generate a tiny quantity of data, but you deploy those in the millions? Then you have a flood of data. Tiny trickles all come together like a river that is a massive torrent when you've compiled all of those together. So there's some really interesting challenges in the IoT space. But that's not really where I want to focus. I want to take a look at another type of embedded system. This is an embedded system that is a little bit upscale from that. And if you can picture, embedded systems will go all the way from those tiny little sensors running on minuscule amounts of energy to fairly large and complex systems. Consider the embedded computer built into an industrial robot. So a system like that may be doing some pretty complicated work. It will have a lot of different sensors, pressure sensors, positional sensors, perhaps even machine vision systems. And that device or that control system needs to collect a lot of input, do a lot of analysis, and it's a much larger system than the tiny one at the other end. And yet, both of these systems, with a little bit of exception on the high end, both of those systems operate largely in the same way, year after year, with little change, right? Your tire sensor is not something that you need to update the software on. The way that we collected tire pressure data a few years ago is the same way that we're going to do it 5 years from now. That's a fixed function device. To some extent, maybe to a slightly lesser extent, the industrial robot will be the same thing. You'll have it working on putting chairs together, and it will just happily do that until you have an industrial designer that modifies your chair slightly. But basically, it's sitting there doing the same task all the way through. OK, so embedded systems, there's a wide range of devices, and we seem to be expanding down into the tinier end of that range on an ongoing basis. Let's put that aside for a moment, and let's look over at enterprise systems. So enterprise system from a software point of view is a system that provides core functionality to run your company or your educational institution or your government or whatever your particular enterprise is. But from a hardware point of view, an enterprise system has certain characteristics. We expect that an enterprise system these days be well connected, that you can access the data from any of the geographic locations of your particular enterprise. We expect it to be there all the time. You don't expect to walk up to the desk in a hotel and they say, oh, we don't really know whether you've reserved or not. You expect to be able to present your name and they'll have all the details of your reservation at their fingertips. And so there's some qualities of the system that go with that. And let me just propose a few of them here. These are the kinds of things that I would expect to see in a real enterprise class system. Pretty significant levels of compute. You don't expect to be waiting around a long time for reports or data retrieval or those types of things. You expect that such a system will have good compute performance. Error-tolerant memory. So if something is wrong in the memory subsystem, you don't get renamed, your reservation doesn't get moved to a different continent, that there's automatic recovery from those sorts of things. You expect things like redundant power and cooling. That if you buy an enterprise system, it's got 2 power supplies in it, it's got multiple fans, it's, as much as possible, been engineered to avoid single points of failure. You expect high volumes of input-output, much higher than you'd have on your personal computer. Your personal computer has maybe at most a 1 gigabit connection, but enterprise class systems, you would expect to have high capacity connections. They would be the type of system that would be accessed by thousands of web users or thousands of internal users. And so you've got an entirely different level of network connectivity and probably some redundancy there as well. Predictive failure analysis. The better enterprise systems have analysis when something goes wrong. If there's a problem with the memory chip, then an analysis system kicks in and says, that's the 3rd memory error that we've had at that particular location or in that particular page. We'd better mark that page as suspect or mark that particular chip as suspect. We'll route around it. We'll use different pieces of memory because we expect that may fail. The same with the disk. If a disk has thrown a couple of errors, a predictive failure analysis system will usually kick in and say, that disk is below threshold. I don't think we can trust it. Let's start using a hot spare and we'll rebuild our storage so that we don't need to use that potentially failing part. An enterprise system will often have accelerators. So for cryptography or for particular math operations or encode and decode operations for streaming video or what have you, there may be dedicated hardware to do those particular things, optimizing it for a particular workload. We'll see redundant storage arrays. We, until recently, have stored stuff on magnetic disks, which sounds great, unless you rename them as spinning rust. because iron oxide is rust. You're spinning a piece of rust at whatever it is, 7,200 RPM or 10,000 RPM, and you're entrusting your critical data to this spinning rust. It's a mechanical device. The only thing that you know about a hard drive is that it is guaranteed to eventually lose your data. So we make that somewhat less likely by storing our data on multiple pieces of spinning rust, or these days, multiple pieces of flash memory. What else do we have in there?
I just said that can also give out. Your USB key can only be written 1,000 times. Yes,
yes. And so we've got issues with flash as well. Typically, you would have some hot standby processors. So you would have, in the more complex configurations, you would have a standby machine ready to assume responsibility for a machine that fails. So a machine overheats or gets hit by lightning or what have you. Another machine is on standby. It should kick in, and you should have migration of functionality to that device. And for a mission-critical environment, one in which you're betting your million-dollar, multi-million-dollar, billion-dollar, multi-billion-dollar company, you want to ensure that the software on that is controlled. So you usually have very rigorous mechanisms in place to ensure that software updates are secure and so forth. So this is not an exhaustive list, but this is, I think, a list of some of the typical features that you would see in an enterprise computing platform. Now, this sounds like overkill for an embedded system. Doing this for your tire pressure sensor doesn't make a lot of sense. However, we're starting to see embedded systems go into some very, very interesting environments. Which of these features would you not want in your autonomous car's computer system? In a context like that, where lives are on the line, especially yours if you're inside that vehicle, it makes sense to take some of these concepts from an enterprise context and use them in what is effectively an embedded device. That's not a general purpose computer. That's a computer that's designed very specifically for a particular task, a particular workload. And you want a lot of those same high availability, high performance features in that particular context. There are a range of other embedded systems that have features that are not typical traditional embedded system features. And an example of that would be, for example, an industrial device. So we've been doing some work with an industrial unit. The predecessor model had a 2-line LCD display and some push buttons, so you could change a couple of settings on it. It had no network capacity. It had no software updating capacity. It had no ability to save data to removable media. It had no local analytics, none of those sorts of features. We're working with that company to update that system so that it has a 64-bit quad-core ARM computer in it. And that 64-bit computer presents a color touchscreen interface. It has a network connection for remote support and for remote data dumping. It has removable media options as far as USB. And it will, in due course, have some advanced options for local analytics and for some on-device machine learning. So there's a whole different level of compute that is being applied to an embedded context here. That's not as critical a context as you would have for, let's say, an autonomous vehicle. But it is still a context that has a number of features that even just a few years ago we would have seen more in an enterprise system than in an embedded system. So what's the significance here? What does this mean? I think that there's several significant impacts of having this technology move down into the embedded space. One of those is that the infrastructure that we've built around the technology, and that and I'm not talking there about technology infrastructure, I'm talking about standards and process infrastructure. A lot of that doesn't exist in the embedded space. So there is no standard way to boot an embedded system. Well, there's no broadly adopted standard way to boot an embedded system. We have that in with industry standard enterprise systems, right? There's well-defined ways that that system should start up, how the software should load, and so forth. We need to take some of the thinking around that. We need to take some of the thinking of support for a standardized platform and take that into this sort of super embedded space. We need to take security a lot more seriously. It's true that you will never update the software on your tire pressure monitor, but in part that's because the communication with that device is outbound only. It gives you information, but it doesn't really receive information. And there is really no chance that a hacker is going to target your device and break in and override your pressure settings. But that's sort of a minimal case. There are many other devices where we are adding a lot more intelligence, and those devices are becoming potential targets for attack. So consider the damage that is possible from attack. Think about this. A thermostat in a house for decades was a little electromechanical device, and you probably grew up, or your neighbor had one of those round things that you just turn to set a particular temperature, and there was a bimetallic spiral spring inside it and a little mercury capsule. So much for reduced hazardous materials. There's a little mercury capsule inside glass in there, and as it heated up, the little coil moved, and if the combination of the amount of movement of that coil and the position that you set on the dial happened to pass a threshold, the mercury flowed to one end of the tube, it shorted some stuff out, and your furnace came on. More recently, we've put a very simple embedded system into thermostats. So through the 90s and the 2000s, you had thermostats where you could set a schedule. You could set up when you're going to be home, when you're going to be away. Some super basic microcontroller in there just kept track of what the current temperature should be, compared it to a reading it was getting from a 30-cent thermal sensor, and again made the decision, well, based on that temperature and the setting that was supplied by the user, the furnace or the air conditioner should be turned on or not turned on. Those were a bit more expensive. Where the electromechanical device might have been worth 20 bucks, the fancier one that you buy in the 90s or the 2000s would be maybe a $40 device or a $35 device. But these days, you walk into a Home Depot and you go looking for a thermostat, what do you see? You've got this nice display of devices from Nest, right? And they're on their third generation now. All of them intelligent devices that interface into your network and attach to some cloud services and actually provide some useful services. You don't have to teach them what your schedule is. They'll learn it. They'll have presence technology, they'll interface with your apps and some other things. They'll learn when you're home. They'll learn from when you turn up and down the thermostat what you like, and they'll do that. But they'll also communicate with you. They'll notify you if something's wrong, your furnace isn't working, and you've got features like that. What the product manufacturer likes about that is that they've turned what was a $20 device into, for Model 1 of that, a $250 device, or for the new Model 3, a $330 device. So we've got a significant increase in functionality, but we've also moved to a situation where we've had a significant increase in price. Well, let's think about that. Even the embedded processor version of that thermostat was not something that you could really, that you had to worry about external attacks on. But an internet-connected, cloud-based singing and dancing thermostat is potentially something that somebody could externally hack into. If you can set the temperature with an app on your phone, then there's no reason that somebody couldn't attack that device, figure out how to set that, and have that control. Now, what's the worst that could happen? They could turn your house into a bit of a sauna, I suppose, and that would be uncomfortable. Perhaps more dangerously, if you weren't home, they could freeze out your house, right? They could set the temperature low or turn the furnace off, and you could have burst pipes and that type of thing. But there's certainly a security element to this significant increase in the capability of embedded systems. So a couple of things here. There's the need for security, especially as far as software updating and remote access. There is where was I a second ago with that? So we've got the need for the enhanced security, but we have other features that we've used in the enterprise space that may be useful, even in a thermostat, because of the importance, at least in our climate, of protecting your house with your thermostat so that you don't burst pipes and cause $50,000 worth of damage due to flooding throughout your house. That's actually a fairly mission-critical device. So how do we address that? How do we make that device really a high availability device, right? We talk about the difficult to attain 5 nines, 99.999% uptime for enterprise systems. But what does that mean for the embedded systems, the connected, smart embedded systems that we're starting to surround ourselves with? We would probably expect better than 5 nines reliability out of the old mechanical thermostat. We should probably expect something similar from the new electronic system. But it's difficult to attain that level of reliability without a fairly high cost. So how do we do that? How do we take the technology pieces that have given us some of these features in the enterprise space, and how do we bring that into embedded systems? At the same time, not completely blowing the budget. $10,000, probably a little high for a thermostat that's sitting on your wall. I think it's important in this to consider. The value of what can go wrong. So, the worst thing that can happen, I would expect, with a thermostat that was hacked, I can see probably 2 bad scenarios. One is that your house is frozen, your pipes burst, tens of thousands of dollars damaged that way. There's also the possibility that the presence detection system in that could be used to leak information to somebody that wanted to, let's say, physically go and steal stuff from your house, right? The fact that you're home or not home is actually valuable data to some people. So there's a couple of pieces there, but really, if you do a sort of risk evaluation, it's not huge. Take a look at the autonomous vehicle situation. What can go wrong with an autonomous vehicle system that fails? What should happen? What should happen? What is a shutdown? What does a blue screen of death look like for an autonomous vehicle doing 100 kilometers an hour down the 401? You would hope that it would involve graceful shutdown, right? You would want a situation where it would fail safe. So when it fails on the safe side, which would probably be to, whatever, pull over and coast to a stop and turn the 4-ways on or something like that. But if you think about what a safe failure looks like, it varies enormously depending on the context. So for a drone, let's say maybe a heavy drone that's carrying a high-definition camera for a movie shoot, stopping is not a good fail state for a drone. Just turn everything off. That is not a good fail state for that. It's going to drop out of the sky, smash somebody on the head, and probably kill them or land them in hospital. So there's some thought needed here. What is the risk? How much do we need to spend to get the level of reliability that we want? How many of these features do we need to bring into that particular super embedded context to provide the reliability, to provide the safety, to provide the performance guarantees that we really need? And what does it look like? How do we picture the worst cases? How do we plan for that? How do we make sure that a worst case results in a safe failure? This is something that we can learn, an area where we can learn from the nuclear industry. They have for years, as part of the design principle of nuclear reactors, had this concept of fail safe. If it's going to fail, and there's two ways to fail, the safe side and the catastrophic side, you want to have sort of the default position to be failing on the safe side, right? And again, as I say, the definition of what's safe varies enormously. It could mean stop. Maybe stop is not safe in other contexts. So there's a bunch of pieces here that we need to bring together. In a lot of cases, what we need to examine is the cost of bringing the features that we need for a particular level of reliability and safety to a particular device. This is necessitated by, as I've said, the advancement in capacity and advancement in the ability of these embedded systems, plus the connectivity of those devices. We know how to do 5 nines, right? We know how to do 99.999% reliability or better. We've been doing it in this space for a while. It's expensive, it's difficult, it consumes a lot of power. So we have to carefully look at that and say, how can we take selectively particular features from that, use it in the super embedded space, and reach our target as far as the performance, reliability, availability, and so forth of those systems. I think this is an area that is going to receive a lot of attention going forward. One aspect of this, particularly the security aspect, is getting a lot of attention, especially after the attacks the other day on the internet in the United States. And our realization that the very low end of the embedded space is the wild, wild west, right? We've got unprotected systems that go unpatched from unknown sources, and there's a lot of danger there. I think what we need to start looking at as we install these super embedded systems, the very intelligent, and in many cases life-critical systems, we need to look there at the whole range of security and performance and reliability issues that arise. And I think, for those of you who are students or considering a new direction, I think actually that there's a lot of potential and a lot of interesting opportunities that exist in this space. All right. So that was the gist of my message, and I'm sure there are a lot of different angles to this. So I'd like to open it up for discussion. We'll take some questions, and maybe we'll provoke a bit of discussion about this. Yes, Scott.
One of the things that I didn't see in this talk was where you feel about the amplification effect that making these devices network-enabled provides. What I'm getting at is here, let's take an example with your Nest thermostat. A modest installation of 5% of the population would be about 1.8 billion Canadians. That's $1,000 property damage for an individual, but if you compromise the whole system, that's a few $1 billion of property damage.
I agree. I think your numbers are a bit high because you're counting population, not buildings.
True.
But right. So the application.
How does that fit into what we should be focusing on here?
So the question, just to repeat it for the audience, the question is, how does amplification affect the fact that you have large quantities of similar systems being installed impact this? And in particular, in terms of risk analysis, what is the impact of having hundreds of thousands, perhaps millions of devices that are installed that have similar characteristics? And I would expect that you're asking that question from particularly the security point of view, and less so from the reliability and availability angles.
Run around and change 1.8 billion thermostats isn't practical.
Right.
Changing 1.8 million net digital thermostats has already been proven trivial.
Right. So let's consider that for a moment. Wherever you have a common organism existing in nature, disease can rip through that population quite easily, right? You've got a monoculture, you've got a population with the same vulnerabilities, and they're susceptible to the same sorts of things, and an infection will rip through. We can see the same thing with digital attacks, right? If you've got large quantities of systems with the same properties, susceptible to the same problems, then obviously an attack against one of them can be an attack against any of them. And the network effect becomes very significant there. I think one thing that you will have almost zero disagreement about within the technical community is that it's essential that any network connected device be upgradable. It's almost guaranteed that there will be bugs in that software. The real question is, how serious are those bugs and when will they be exploited, not whether they will be exploited. It's also generally accepted that there's not a lot of incentive for either the producers of those devices nor the consumers of those devices to keep the software up to date. A company that, well, in the case of the recent internet attacks, right? One company produced a range of network-connected cameras and digital video recorders. They sold these to other companies that branded them and packaged them in their own fancy casings and sold them on. Now, no one in that ecosystem really cared about software upgradability, right? They just wanted to pump the devices out, get them installed, get the money from it, and that was it. Likewise, the users of those cameras, the small business that has 5 or 10 or 20 of those network-connected cameras, if you approach them and say, you're going to have to rip all of your cameras out and replace them with new ones so that Twitter can stay up, they're going to say, what? No. I'm not replacing my cameras. I'm not spending a couple of $1,000s to replace the cameras to keep Twitter alive. That just doesn't matter to me. So there could be some actors in between that come into play. You could have, for example, ISPs cut off service to customers that operated insecure devices. That's a pretty hard line, and that's maybe not really attractive to the ISPs themselves to play the role of cop. But there also seems to be a fair bit of agreement in the industry that one of the significant ways forward there is to stop inventing our own unique solution to every little connected device, right? To use common platforms. This is where we see projects such as Zephyr having a significant value. Common open source platform that can be used across a wide range of devices with, a little bit of secret sauce on top for the particular device that is being installed, with standardized, secure updating mechanisms so that it becomes much less expensive for the vendor to offer those security updates. And it actually becomes much less of a hassle for the consumer to accept those updates, to have them downloaded over their network. It's done automatically with a small amount of data and without significant cost to the consumer. So I think one of the important pieces going forward in security, from the Internet of Things range up to sort of the mid-high super embedded range, is going to be standardization. Right now, we've got the wild, wild west, right? How many of you have a Wi-Fi or Bluetooth-enabled light bulb in your house? Okay. This is a little bit of a fringe case, right? Those light bulbs probably have their own unique app and their own unique protocol, right? Every other little residential IoT device has probably also got its own silly little app and its own gateway protocol and so forth. And so it's wild, wild west. We're too early to really expect standardization. We've had a bit of innovation and we've got some forward movement. But please, let's not wait longer before we converge on a small set of platforms, on some gateway standards, some communication standards, and some best practices for the management of security there. Yes?
You're so optimistic. On the desktop, we standardized on craft. And that was a system where people were thinking about it. People don't think about light bulbs and so on. What are the chances of standardizing on a grid system and not a craft system?
Excellent question. So the point is, on the desktop, we standardized on crap. And yes, we did. Absolutely. I don't think you'd find a whole lot of people that would argue with that. However, in the enterprise space, we've tried to standardize on something a little better than complete crap, with mixed success, right? So I think what we need to do is, as an industry, first collaborate. If we independently try to come up with mechanisms to do what we want to do, and again, we're largely focusing on security here. If we try to independently implement a secure updating mechanism, we're wasting a ton of effort. Most of us are probably going to do it wrong, and we'll end up with a very expensive hodgepodge. And so, as I mentioned, the Zephyr project, there's others such as Embed and so forth that are moving towards standardized platforms. And if you are an embedded product producer or developer, we're getting to the point where it really doesn't make any sense. And in fact, I'm thinking we're probably still a year or two out before it becomes absolutely a no-brainer decision to use a standardized platform, just because reinventing the wheel is going to be too expensive. That's really where we are with the Linux kernel, right? Are you going to write your own kernel for a particular application? It makes no sense, right? Take the billions of dollars of work that have already been done on the Linux kernel, add something to it, and you can use that as a platform for an advanced intelligent system. Scaling down from that, more towards the tiny IoT device end of the scale, we need a similar solution. It's got to be open source, industry standard, but smaller. It's got to be a platform that can run on a system smaller than what you would want to run Linux on, smaller than what you would want to run BSD or some of these other standard larger platforms on. Yeah?
Just a question would be, in the world we live in, how do you fight the bottom line? Because everyone's trying to go for parity to kind of, ease their bottom line. How would you provide an incentive to move away from that mentality and learn to collaborate, force people to share ideas, sort of?
It's a very good question. How do we teach? But let me turn that around and say, in a general sense, how do we teach corporations to be responsible? And if we look at things like forestry, right? How did we convince paper companies to use wood pulp from sustainable forests? When you look at, hopefully, if you look at your cup, and I'm hoping that these cups have it on it, you'll see these days on paper products the Forestry Stewardship Council symbol, right? And so what made a change there was that we, by raising public awareness and almost by shaming the non-compliant companies, we developed an expectation around what the corporation should be doing. And I think that we need to, as consumers, demand that of providers of technology to us. Conversely, when we're making the argument to our own companies, we need to make that same argument. We could release this non-updatable, we hope it's secure, but we really don't know, embedded system. Or we could do it right. We could use an industry standard platform so that when those bugs are ultimately found, there's a mechanism in place for it to be updated. And by working with the industry standard platform and that consortium, we can cut our costs, right? We will contribute towards that, but it's going to be a fraction of what it would cost us to develop such a quality platform independently. And so I think those are the two angles we have to come at it. The one is share the load so that you're not bearing the full cost yourself, but also there needs to be some pressure on the industry players to say it's not acceptable that you're shipping non-updatable firmware. That's, you know, in fact, we're not going to buy a device that's got those qualities. Adrian.
That was a long answer, but the last sentence I think sums it up. Don't buy. Because they provide a service, and they figured out what's more cost effective for them. If using paper is more cost effective and you're buying, then there you go. We cannot really blame the companies before blaming ourselves first as consumers. So it's a very, very simple answer.
But what complicates that, what complicates that is that we never had to think about that with the predecessor devices. So the predecessor to that smart thermostat, you never had to worry about whether it was updatable. The predecessor to the industrial device that we were working with, you never had to worry about whether those things were updatable. So it's not in our consumer mindset to think about some of those pieces. And I think we need to become better educated and more effective in swinging our economic weight around. Yes?
So with regard to that kind of point, what do you think the role of regulation is in this? When you're explaining what you were saying now, I was thinking about the restaurant green sign thing in Toronto. The city evaluates every eating establishment and gives them a red, yellow, or green pass.
Right.
Is the government or some body, is there a role for them to play to evaluate all the thermostats and all the drones and everything and give them a green security gate?
So here's a question. Given the choice of having the government step in and try and devise an up-to-the-minute program for ensuring safety in embedded systems, or having the industry do that directly in response to economic pressure, you take a look at those two things and you think, which moves faster, which is going to end up being ultimately the most effective? And I would agree with you that we probably need a combination of those two pieces. But I think in a lot of cases, the government, if you look at the government policy on internet connectivity and other things, they're struggling to keep up with the state of the technology.
Like health standards don't change the same way the protocols do.
Right. Right.
There's a mechanism that might be perverted to do that, and that's underwriter lab and CSA approval. They could say it's a requirement. They could expand to say it's a requirement for digital devices to be updatable. And there's a process for recalls of defective, dangerous equipment. These can maybe be mutated without drastic institutional changes to do what you're talking about. But I think you're right. It takes every approach, not just one approach.
Right. Interesting that you mentioned underwriter labs. You see the UL certification on many electrical devices. An underwriter is somebody that's insuring something. And actually, it's interesting to the insurance industry that the devices that you have in your house and business are safe. And actually, if there is a liability to the insurer for some of the digital risks that we are encountering going forward, then that may actually be an avenue to put some pressure on those companies to toe the line. We've talked a lot about security, and I want to just, in closing, draw attention to the fact that this is about more than security. On the small IoT range, security, yes, that's important. But there's other important features here, and this is really where I was talking about the enterprise angle. There's other important features that we need to pull in. We already know how to do high availability. We already know how to do predictive failure analysis. We need to bring those technologies from that one scope into this super embedded space. So, Andrew.
In terms of standardization, you mentioned the Linux kernel, and I'm not sure I see the parallel, because the kernel, I think, was as popular as it was because it's a general purpose system. Like, you can use it on a cell phone, you can run it to a server farm, and everything in between. With embedded systems, you have 10 million unrelated separate systems that don't really go together. They can't go together because they have to be so small. So what are the chances of arriving at a consensus when you all have different goals and not much overlap?
So let me draw a box around that. The vast majority of deployed small embedded systems are going to be running one of a very small handful of processors, right? It's going to be something in the ARM Cortex-M or possibly Cortex-R family, or there's a couple of other alternatives to that. And ARM has a huge market share, but there's some other companies that have significant market share. So you're not dealing with hundreds of diverse architectures, right? You're dealing with a fairly small set. You're dealing with very similar requirements, right? A sensor-style IoT device has some kind of sensing that's unique to that device, and then it's got a communication stack. It's got TCP/IP or Bluetooth or Zigbee or whatever. It's got a standardized communication stack that every other device that uses that same protocol has the same stack, right? So there's a bunch of common software pieces. The underlying piece, the scheduler, the event loops, if you will, the communication protocols, and that is probably 90+% of your software stack. And then you've got the little piece of code there for whatever it is that you're actually trying to sense. So why not collaborate? Why not share the cost of developing that 90% piece of code with the rest of the industry rather than building your own thing that you have to maintain forever as an independent company? Yeah. And one last question.
Do you believe in the future of artificial intelligence? Because now lots of companies invest billions of dollars into this technology. And what's going to be next?
So if you rewind a couple of decades, artificial intelligence was a non-starter. We didn't have the horsepower to make it happen. Recently, so we put it on the shelf, right? We put AI and neural nets and all kinds of stuff on the shelf. And recently, over the past few years, we've dusted that off. We realized, hey, we've got the performance levels where we can pull that technology that we were working on years ago and we shelved. We can pull that off the shelf, dust it off, update it, and we've got the levels of performance where we can actually do some real machine learning, some real neural networks, some, all of those related technologies. So whether you believe in it or not, it's here, right? It's something that's in use. It's a significant part of our digital economy and our digital lives. I'm not sure that that's going to lead to the singularity in the very short term, but I don't even think there's a question of do you believe in machine learning. It's here. It's part of our lives.
The time when computer programs can reproduce the computer programs.
Right. And there's a threshold there, right? As soon as you make a program smart enough to make itself, and then you go one step beyond that, then potentially you've got the death spiral. And fortunately, there are some people like Elon Musk and some companies like Google that are already planning in kill switches from the beginning. And so that's a kind of interesting development in that space. All right, thank you very much for your attention.